same group, of course, is Linda Tacconi.
Thank you very much. Let me just get... Okay. Okay, can you hear me? I'll try not to put this too close. So it's great to be back here. It's been 2 years since I've given you an update on where we are with our studies of molecular gas in high redshift galaxies. And what I'd like to tell you about in the next few minutes is the latest results on what we think are fairly robust scaling relations of molecular gas fraction and gas consumption time as a function of redshift, specific star formation rate, stellar mass, and galaxy size. So this is work being done with a large group of people. The FIBS team, which I guess Jonathan Freundlich told you about, the FIBS survey on Tuesday, so I won't go into that. And at low redshift, we've combined efforts with the cold gas team, which was a huge survey of CO in redshift 0 galaxies. So the three techniques, we're now able to cross-correlate three techniques with CO, which we're using the IRAM-Nuema telescope, Herschel far-infrared SEDs, and now with ALMA, we can also use 1 millimeter continuum long wavelength emission from ALMA. So I'm going to tell you about, this is these various surveys in our compilation, both from our own work with FIBS and Herschel, but also we've taken much work from the literature, from Nick Scoville's work, from some of the other CO surveys, and we have very good coverage from redshift 0 all the way out to almost redshift 4. And the coverage is shown here. So what this plot shows is as a function of specific star formation rate and redshift in each panel. This is our coverage. So this is the main sequence as a function of redshift from the 3D HST work in color. This panel shows all the CO points that we have. The black points are from our FIB survey. These red and magenta points are from various ULERG and submillimeter galaxy surveys. As comparison, we wanted to see, as you go across the main sequence into the extreme starburst regime, how things change. And these green points are the 400 plus galaxies from the cold gas survey at redshift 0. In the middle, you see our coverage of the Herschel far-infrared dust technique, where you fit SEDs to the far-infrared points, and you apply dust mass models to get and then a gas-to-dust ratio to get a molecular gas mass that way. So the Herschel coverage is also fairly good, with the caveat that above about redshift 1.5, with Herschel, one needs to stack many, many galaxies to get a result. And then finally, these are the points that we've included in our scaling relations, which are now published here from ALMA, mostly from the literature. So what is different about this work from other works? What we have tried to do here is to cross-calibrate these three methods using consistent methodologies in deriving star formation rates and stellar masses and molecular gas masses. So we've made consistent assumptions across all the different surveys, adjusting parameters when necessary. And when we do that, the key point you should take away is that much of the discrepancies that exist in the literature vanish. A lot of those discrepancies come from the assumptions people have made about CO conversion factors, the different ways people calculate star formation rates, and the different ways people are even calculating stellar masses. When you do it all in a self-consistent way, things actually are fairly consistent. I should also mention there's another paper recently from Nick Scoville and his group that is including 700 or so galaxies using just the ALMA 1 millimeter technique. And it's really reassuring that the two results of these two papers now are almost are completely consistent. So I think we're getting to a point now where molecular gas studies are becoming very robust. Wow, okay. So let me start with the first scaling relations. Those are the ones of gas depletion time. And what we have here on this plot depletion time as a function of redshift, as a function of offset from the main sequence, where these are the starbursters down here, and these are below main sequence, as a function of stellar mass, and as a function of size. And the relation is shown here. But what you can see, the points here are just binned averages using the different techniques. The black points are always CO, and the various colors are the different dust studies from the literature, either Herschel or ALMA 1 millimeter continuum, and the underlying, all the data points are in these color contours. So what you see is we see a very shallow fall off of depletion time with redshift. This was surprising to some. We find average depletion times on the main sequence of anywhere from a gig a year or 1.2 gigayears at low redshift to a little under a gig a year at higher redshift. Our tightest correlation is with offset from the main sequence, which is this correlation here. Once you subtract out the redshift dependence, you get a very tight correlation between specific star formation rate or offset, the depletion time, and correlated with offset from the main sequence here. When you subtract that off, you can see that there is very little leftover correlation with stellar mass until you get to very low stellar masses, which I'll come back to in about 30 seconds. And surprisingly, we just using the CO method now, because we need to get good, we need something with we're using optical sizes. Surprisingly, we see very little correlation of depletion time scale with size, which I'll come back in my summary with perhaps why that might be. So here is our tightest correlation here with depletion time as a function of offset from the main sequence, and you see this is our global fit in the dotted line here. And one point I just want to make is a slight technical point. We're using a CO conversion function that does not go up. It has a metallicity dependence at low stellar mass, but it does not, what we do not do is use a so-called Euler conversion factor in the starburst regime. And if we were to do that, we would see that these black points would go up here. And you can see that here with our conversion function, the dust methods and the CO method agree very, very well. And so we now believe, and Nick Scoville would agree with us in his latest paper, that this conversion factor in the Euler regime doesn't actually, we see no evidence for it at high redshift. At the low stellar masses, another technical point, these various lines show if you adopt different gas to dust ratio or different prescriptions for metallicity in the low stellar mass regime, you will see different fall-offs. This is our best fit here to the points we have so far. And you can see that below about 10 to the 10th solar masses, you start to run into a lot of trouble with making the right assumption on metallicity. And that affects not just the CO measurements, it also affects the dust measurements, because you have to assume some gas to dust ratio dependence with metallicity, which is very uncertain, especially at high redshift. So let's do the same thing now with molecular gas fraction, which is just it's related to the depletion time by this relation here. So it's just the molecular gas divided by the stellar mass. And again, you can plot it as a function of redshift, offset from the main sequence, and stellar mass. And so you first see that the redshift dependence is a well-known, by now, a relation, which is roughly to the 2.5 power with Redshift, where typical galaxies at Redshift 0 have molecular gas fractions of on the order of 10%, and a typical Redshift 2 galaxy is about half molecular gas. You can fit out the redshift dependence again, and we see another tight correlation here with offset from the main sequence. That is, as you go above the main sequence, you get also higher gas fractions. So as you go up in this regime, you get not just a higher star formation efficiency or a decreased depletion time, but also an increased gas fraction. That may be because some galaxies that bring them up above the main sequence happen to just recently accrete something, or maybe the gas was somehow efficiently channeled into the regions that we're sensitive to. Then finally, you can subtract this dependence, and you plot as a function of stellar mass. And then you see that it's reasonably flat, but you see this drop off in molecular gas fraction once you get above the Schechter mass, which has been seen at Redshift 0 in the cold gas surveys. We've seen it before in our earlier FIBS work, and with these 1400 points, you see it very clearly here as well. So we think that is tracing somehow the start of quenching of star formation once you get above the Schechter mass. So the summary for the scaling relations, and then if I still have a few minutes, I want to make a couple of comments about the Kennecott-Schmidt relation. These two plots up here sort of give our overall summary, which is, this is a plot of specific star formation rate relative to the main sequence as a function of stellar mass. And the color coding is the depletion time trends and the gas fraction trends after subtracting out the redshift dependencies. So what you see is, or what I've tried to tell you so far, is that the dust and the CO techniques agree very well on the main sequence and for roughly solar metallicity galaxies. Below solar metallicity, which is why many people have avoided going to low stellar mass, things become much more difficult. And it's a very big caution to people who are trying to go to high redshift, very high redshift, because the mass metallicity relation is going to kill you up there with both the dust and the CO techniques. You're going to have a lot of trouble trying to calibrate that. But, you know, it's just something to keep in mind. You can get these global relations once you have the broad coverage and the large number of sources. So we believe you need on the order of 1,000 or more sources to really be able to pull these relations out robustly. We don't see the evidence for the strong alpha CO variations in the starburst regime. We see a very shallow variation of depletion time with redshift and stellar mass, and the gas fractions trace a specific star formation rate with redshift, which we believe tracks the accretion rate onto the galaxy. The gas fraction is typically quite high at Redshift 2, 50%. We've known that for a while, but it's important to keep emphasizing it. And at a fixed redshift, as you move up in specific star formation rate, perpendicular to the main sequence, the depletion time drops and the gas fraction increases roughly in equal measure. Finally, we see the gas fraction with stellar mass drop. With stellar mass, especially above the Schechter mass, perhaps due to inside-out quenching of galaxies. So just very, 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 very quickly, the Kennecott-Schmidt relation, in its original form, has a slope of 1.4. And this is the plot from the updated Kennecott and Evans paper, where they have included both molecular and H1 using a wide range of redshift 0 galaxies and a constant conversion factor. And they came up with the slope of 1.4. But other studies, in particular the spatially resolved observations of Leroy and Biggiel et al., showed a roughly linear correlation when you use just molecular gas, and no correlation when you include H1. And so there's been a lot of debate whether to use linear, whether to use 1.4, what to use. And this is especially important because I know it's used a lot in recipes for simulations. So what we've done is tried to make mock data using our scaling relations now. And what this plot shows is just 50 random Redshift 0 main sequence galaxies. Like the big eel sample, you see roughly a linear relation. If you add in some high redshift galaxies with our scaling relations, you see the difference between this, the linear, it still stays roughly linear. When you add in starburst galaxies, which is down in this bottom row, this is now at redshift 0. When you add in starburst galaxies, you now get the superlinear trend, which is reflecting our the fact that the depletion time is decreasing. And if you draw a fit through that, you're going to get your 1.4 slope. The thing to keep in mind is these are rare beasts, and the plots that have been in the literature so far and this plot contain an overabundance of these starburst galaxies. If you want to really trace the population, you would only have 1 or 2 of these. Your slope would go back to something more like this. So be careful with the Kennicutt-Schmidt slope. And then also if you add in then H1 on top of that, this is what you get, and you again get a steepening slope. So with that comment, I'll just stop here. Thanks.
Okay, great. So there's time for some questions. Okay. Oh. No questions? Go ahead.
What's the fraction of atomic gas that you are adding?
This is just a constant 10 to the 9th solar masses of atomic gas, which is a rough average at redshift 0 for a typical spiral type galaxy.
What is the ratio between molecular and atomic hydrogen that you are adding?
Well, the molecular will come from the scaling relations, and the hydrogen is just a fixed amount of 10 to the 9th.
Yes? Richard?
Great talk on great results. How would you interpret, I think you explicit all the things you mentioned, but how would you interpret these kind of results, variations away from the specific star formation rate, the main sequence, star formation rate? Just looking at, I think you were saying it was largely due to gas accretion, but just looking at the results, it suggests that it's partially due to the change in the gas fraction, which probably is due to gas accretion. That's half the effect.
Right.
The other half is due to some change in some variation in depletion time.
Right.
There could be some other physical mechanism.
Well, it could, I mean, yes, there are various, there could be a larger fraction of, a larger dense gas fraction, which is something we haven't really been able to investigate because we have just CO and dust. So there could be one idea is that the dense gas fraction goes up at high redshift. And we don't have a quantitative estimate of that yet.
Yeah, but I guess this is something that would be great to completely model. The results are just fine for comparing with some of these simulations.
I agree.
We actually look into this in the simulations. We reproduce these trends in the sense that indeed that in the galaxy, it's a lot of gas in percent region, the gas density increase when your stuff efficiency or depletion times.
So that's a paper by Sandro Cicella published last year that shows that the Vela simulations are exactly consistent with the trends. In fact, all 4 of the trends. Okay, well, thanks to